Hello everyone. Today we're gonna start our chapter 16, the last chapter of our Calculus 3 course. I'm gonna start our video clip today with the first two sections. 16.1 is about vector fields and 16.2 is about line integral. So let's start with 16.1. I'm gonna give you an introduction into something called the vector fields. Okay? So vector fields, I think the name implies something. It's a field of all the vectors. And what I want you to think of is what is a vector functions. So for example, I define a vector f, say in 2D, okay, two-dimensional, and of course by similarity you can think of 3 or 4 dimension or 5 dimension, doesn't matter, n dimension the same way. Vector f x y is defined by 2x plus 1. This is a vector, comma y minus x, for example. Okay? So, if you plug a point xy, this is the xy plane, all right, 2D. You're going to have a vector at that point. So if I plug an f 0, 0, I plug an x equal to 0, y equals 0, I have a point x0, y0, so it's going to be 1, 0. Because 2 times 0 is 0 plus 1 is 1, and 0 minus 0 is 0. So what? At the point 0, 0, the origin right here, we have a vector 1, 0. X is 1, y is 0. Vector is right here. Okay? Try another one. Say f 1, 1. I plug an x equal to 1, y equal to 1 in here. X is 1. I got 3, 0. I got another vector. At the point 1, 1 right here, I got a vector 3 for x and 0 for y. 1, 2, 3 for x, 0 for y. Oh, I put it wrong. I'm sorry. It's not right here. Let me draw. At the point 1, 1, the point 1, 1 is right here. I have the vector 3, 0. This is the vector. Okay, this is 1, 2, 3, 4. 3 units to the x and 0 unit for the y. So 1, 2, 3 units to the x and 0 for the y. This is the second vector. Try another one. Say f 0, 1. Let's just make up a point. X is 0, y is 1. So what? X is 0, y is 1, right? So the first point is 1, 0 times 2 is 0 plus 1 is 1. And y is 1, x is 0, 1 minus 1 is 1. 1, 1 again. At the point 0, 1, the point 0, 1 is right here. I have the vector of 1, 1. 1, 1 is this one. Go 1 unit to the x, 1 unit for the y. Okay? This is how we have vector functions. So similarly, if you plug more points, you have more vectors. So vector field is a field of all the vectors. And as we learned before of vectors, vectors got two components. One, the length, the magnitude, so how long, how strong a vector is, and the direction, right? Two things. Okay, and similarly, if you have a 3D, then 4D, 5D, then you have a vector on a bigger dimensional space. The same idea, okay? And usually, people, just our book tradition is right what? Say, vector f, say, x comma y, is denoted by what? P, Q, where P is a function for the x component, and Q is a function for the y component. And similarly, if you have 3-dimensional space, and what? X, Y, Z, and it's going to be P, Q's, and what after Q, and then P, Q, R, right? 3. And then of course, X is what? X, P is X, Y, Z, Q's function of 3 variables x, y, z, and r of course function of 3 variables x, y, z as well. Okay, so we have vector field in space 3D. This is vector field in 2D. And the next question you should ask is, what is it good for? Oh, there's a lot of application for vector fields. We use vector field to represent what? The airflow, the ocean current, by looking at the map with all the vectors, all the arrows with magnitude and direction. You can tell how the current's gonna flow and what is the strength of that current. or if you guys study physics, then those terms I'm about to mention gonna be familiar to you guys, like velocity field, what else? Electric field, magnetic field, right? Force field, okay? And that will help us to learn more about applied science. All right, that's introduction to vector fields. And actually, I claim that you guys seen something like vector field before. We call something called the gradient. Gradient. Okay, say you have a function f. I'm right. Give you an example of two variables, x, y. Okay, but you can look at. You guys can look at an example of 3 variables, 4 variables. It's pretty much the same idea, it's just more variables to work with. So let me give you an example. Say fxy say equal to x squared minus 2y. It's an easy example. And recall what we learned about gradient of f is equal to what? df over dx, and then df over dy, right? Partial derivative of f in terms of x, partial derivative of f in terms of y, and you have what? Df over dx is 2x, okay? Df over dy is -2, and you see what? This is really a vector, right? So if you have a vector f of the form gradient of some function, or you say what? If you have a function, vector function f, okay, such that this is a gradient of some function little f above, then we say that this vector field is conservative. Conservative. Okay. Okay. So let me write it down a little bit more clearly. A vector field f is conservative if f is equal to the gradient of some function f, okay, for some f, or some function f. Okay, so this example right here, if I got a vector field f equal to 2x -2, then I say that the vector field f is conservative because f is conservative. Because we can find there is a function fxy, right, where fxy equal to, say, x squared minus 2x plus 1, such that the gradient of f is equal to big F. Okay? One more time, vector field f is a conservative if we can find a function f such that the gradient of the function f is equal to the vector field. Okay. And of course, same idea if you have vector f into 3 variables, 4 variables, the same way. Are we good? And I think since you guys study physics, the word conservative means a lot, right? Conservative of force, doesn't matter what path you choose. Later on we talk about line integral, and doesn't matter what path you choose. You want to move an object from the original point to the initial point, from the initial point to the final point. Doesn't matter what path you choose. You're going to use the same energy, the same work. Okay? Talk about conservative. It only happens in conservative field. Okay, so that is basically a definition, an introduction to vector fields. So to grab up 16.1, what I want to bring to you is what is a field of all the vectors. Okay, and vector has 2 things: the direction and the magnitude, the length of the vector. So think of the vector mathematically. You think of vector as a function. So in here I give you example of 2 variables, or you can have 3, 4, 5 the same way. Whenever you have a point, you can find out, apply it to the plug to the function that you have. You can find a vector at that point. Okay? And by the way, if you have vector, you know how to find the magnitude of the vector. Square root, right? First term square plus second square, second term square, third term square. Okay. Now, let me move on to the second section. Section 16.2. I'll be talking about line integral. So let's recall what you learned in Calc 1. You have integral of fx dx run from a to b. And graphically, say a to here, b to there, right? This is function f of x. And Riemann integral, say what? Integral from a to b fx dx is really the area. Right? So, in other words, we're looking for the area of the region above the line segment run from a to b. A straight line on the x-axis. Okay? Below the function f, above the line segment run from a to b. Okay? So in Calc 3, we're going to extend the concept a little bit more. Instead of just a straight line segment, see, x right here, so the x went from a to b. Let me try to draw it in 3D. Okay? Excuse my drawing, let me try to draw it up. We're going to define something called the line integral on this curve C, anything. All right? F, let's do 2 variables for now, but I claim that the idea is going to apply the same way to 3, 4, 5 variables. ds, okay? S is a curve. C is a curve right here. ds is a little change on the curve. So let me try to draw in 3D. This is my x-axis. This is my y-axis. This is my z-axis. Okay? And this is my function f x y. This is the surface above the xy plane, okay? And this is a curve C in general on the xy plane. This is a curve C right here. All right? Okay. So, what do we mean by this integral? It means this. Watch me close this, see how I draw it. Okay. Okay. Draw it better, make it look like curvy. All right. So you have a curve C on the xy plane. It's kind of looking up, and then it's gonna intersect the perpendicular surface, okay, to the xy plane. Up to the surface of the function xy is going to intersect with that little curve right here. And this is the area that we're talking about. Okay? Okay. So the line integral of fx ds means what? The area is like of a fence. It may not be a straight, like flat like this. Okay, it's curvy. It's curvy. All right. It's of the surface is bounded by what? The curve C right here, and the curve on the surface fxy, and then those bounded by the 2 endpoints. Okay, just like a fence. Hopefully you can imagine my drawing. Okay. And ds is what? ds is a little change on that curve C. So you take a little bit change times the function f, you have a little area right here, and then another ds times function f, you have another change. So what? On the little area, you add all the area together, and that is integral of the curve C right here. C of the function fxy ds. Now, let's go back to D1 a little bit more. So it may not be straight line right here, right? It could be a curve, and then the function f, now it's a function fxy is going to be another curve right above that of C. Okay, recall back to count 1. What you have? ds was equal to square root of dx over dt square plus dy over dt square dt. That's how you learn count 1 for little change of the curve. And this comes from, let's say you have a curve, right? This is C, okay? And ds is the whole curve right here. If ds is that much, this is dx chance of x. This is dy chance of y, and since d is later on we take limits on, we pretend that this is a straight one. By Pythagorean theorem, ds squared is equal to dx squared plus dy squared. Okay, you take square root and divide by dt, you have this. ds over dt squared is equal to dx over dt squared plus dy over dt squared. Take square root on both sides. So ds over dt will be square root of this, and then you multiply both sides by dt. You have the formula. Okay. So this is a definition. This is line integral. It looks like this, and the technique that we're going to use to integrate this one. Usually, we parameterize it. You see right here. Okay, we think x as a function of t, y as a function of t, and then ds, I just erase it, square root of dx over dt square plus dy over dt square dt. Now we bring back to the integral of one variable, t. Okay, so this can be rewritten as integral of f of xt comma yt, and then ds is square root of dx over dt square plus dy over dt square dt, where t run from t0 to t1, whatever it is, or a to b. I try not to use ab because I already use ab for changing of x. Okay. So I think it's good if I give you an example. Example. Calculate the line integral c of the function. I just use the example in the book then. Let me find an example in here. Okay, I give you a very easy example. 2x ds. Okay, where c is what? Where c is a parabola. C is parabola. Y equal to x squared, run from 0, 0 to 1, 1. Okay. So graphically, this is what you should think of. X-axis, y-axis, and this is your parabola. Okay. And we don't look at the entire parabola. We only look at the point from 0, 0 to 1, 1. This is 0, 0 right here, 1, 1 right there. And this is y equal to x squared. And this is the piece of the curve that we're talking about. Okay? And imagine that the z-axis is coming outward. And we have a function, fxy is equal to 2x. fxy in this particular example is equal to 2x. Okay, I think this is the plane up here. Okay, and you want to integrate this. Of course, we have to convert everything into t variables, so parameterize it in terms of t. And this is a very simple way to parameterize it. Think of x equal to t. X equal to t. Then y is t squared because y is x squared. And fxy equal to 2x, this means equal to 2t. Okay? And when the parabola run from 0, 0, x run from 0, 0 to 1, 1, so x run from 0 to 1, so xt, so t run from 0 to 1. The book gives you a very simple example. So this is the integral for t, okay? X equal to t, so x equal to 0 means what? T equal to 0, x equal to 1 means t equal to 1, of course, because x equal to t. So this is the integral from 0 to 1 in terms of t, okay? 2x now becomes 2t. fxy right here, 2t. Now you have to calculate this, right? dx over dt, x equal to t, so dx over dt is 1. Square root, right? dx over dt is equal to 1. dx over dt is equal to 1. 1 squared is just 1. dy over dt is 2t. So this is 2t squared. And then dt. And now you see, line integral now becomes what? Calculus 1 integral, 1 variable. And all you have to do is integrate that right here. 2t square root of 1 plus 2t squared dt. And I guess for this problem, you guys can all do is just use something. Let me see if my claim is right. Yeah. Do a use something, should I? Let me finish that for you. This integral from 0 to 1, 2t square root of what we have right here, 1 plus 4t squared dt. Okay? Let u equal to 1 plus 4t squared, then du, I'm doing use of count 1 technique, equal to 8t dt. Okay? T equal to 0. T equal to 0, change the variable, right? Then u is 1. T equal to 1, here 1, so then u is 5. Okay, so this integral becomes from 1 to 5 in terms of u. 2t is what? Du over 4, right? So 2t dt is 1 over 4 du. Divide both sides by 4 right here. So I got 1 over 4 du, and this one is u right here. So square root u, so u to the 1/2. Okay, integrate u to the 1/2. Plus 1 in here, I got 3/2, so 2 over 3, 1, 4, and 2 over 3, u to the 3 over 2, integral from 1 to 5. I'll stop right here. You guys look at the numbers, you have the answer. Okay. So, this one right here, we say with the line integral with respect to the curve C. Okay? And we write it this way. Line integral of the function f with respect to, I'm just trying to write short here, with respect to the curve C, right? This is how the book writes. Let me go back to the arc length, okay, with respect to the arc length. Which means the curve C, right? Okay. Now, we have another version of it, a little bit different, say. If you have line integral with respect to line integral with respect to the x, and you have this integral of c f of xy dx. Okay, so the variable is not the change of the curve. This is what the variable is, the change of the x component of the curve. And similarly, you have respect to y, then you have this integral c what f of xy dy. Okay, so still the line integral of the function fxy, but now it's not a little change of the curve anymore. Okay. So let me redraw it right here. This is x-axis, this is y-axis, and this is z, right? You have a curve. This is a curve C. Try to draw it better so it's easier for you guys to see. The curve C, okay? So if you project it down to the x-axis, then this is the change of the x value, dx, a little bit of change in the x along the curve. And this is change of y value of the curve, dy. Okay? So ds, you change a little of the curve along the curve, ds. Okay? But you project to the x-axis, the change of dx. Project to the y-axis, the change of dy. Okay? And this is the another integral. Still line integral, but now the change is not the change of s anymore, it's just f. And this is change respect to y. And of course, the way you solve is the simpler case of the general case right here. You still parameterize it. Write x as x a function of t, y as a function of t, and then the x now is differentiable as a function of t, right? Again, the derivative of x in terms of t, and you have it. Make sure that you guys get it. I'll come back to the example that we had before. Okay, we got f of xy equal to 2x, the same example as before. And I remember that x is t, y is t squared, right? So now what? fxy now is fxy is 2x, now become 2t, because I change x to t. And dx is dt right here. So this integral now becomes what? Integral of 2t and then dt. That's all it is. Okay? And of course, theorem from 0 to 1. Right before. And similarly, second one right here, dy is 2t dt. Okay? So this one becomes what? Integral from 0 to 1, right? And xy is 2t, and then dy is 2t dt, and you integrate them. Okay? So ds is harder, right? And you know how to do with ds, then you can do dx and dy. Okay. We tried to find a geometry interpretation of this, but I'm not sure if my interpretation is good enough. Let me try to draw it out. See if that makes sense to you. It may work in this case. Okay. This is my fxy in general up here. Okay, and this is my curve C right here. You project it up, bring it up. You integrate what? fxy ds. You calculate about this area of this surface right here, the fence right here. Okay. And now dx means what? Now you project the whole thing with respect to the x-axis. So the curve C right here, project the x-axis, becomes the line right here. Okay. And that curve right here, project the x-axis, is going to be something above right there. I don't know what it is. Okay. Then you integrate, you calculate this area. Similarly for dy, you project that curve, that little red curve right here, to the y-axis. You're going to have something. Let me just do. There's something right here. Okay. And then from y1 to y2, you're talking about this area on the y. Things that are be more complicated is if the curve keeps moving back and forth, and you have to jump it out into many little bits and calculate. But roughly, that was the idea. Okay. That's about the line integral of a function in two-dimensional. And similarly, if we talk about line integral in three-dimensional space, and just add more variable, and the work going to be longer, but the idea is going to be the same. Say you have line integral of f x y z ds on the curve C. Now I can